Well, hello. This is the first HL video, if we're going through this in order. And we're returning to the ideas of the circle and looking at ideas of sectors and arcs, but this time with a focus using on radians and using radians. And a radian is a unit of measure of a rotation in which it is defined by the rotation required so that the arc length is the same as the radius. And so in this case, we see a radius of 1 and the arc length is also 1. And so that's what 1 radian is. This here, this angle we see is 1 radian. Notice it's a lot different than a degree. And it's much more convenient to work with, especially in topics related to calculus, or in fact, just related to what we'll be doing today. A lot of formulas we've seen before are actually much more pleasant to deal with when we're dealing with radians. That said, first we want to start developing a feeling for what angles and degrees are in radians. And maybe before I look at this, these angles here, 30 degrees being pi over 6, 45 degrees being pi over 4, and so on. These are critical. And when dealing with radians, we see, these are special angles or multiples of special angles, and we see these so often that we should ideally know them, off from your heart. That doesn't seem to make sense. You know them off by heart. That's what I'm looking for. Almost instantly. And it all really goes back to the idea that once we realize that a full rotation is 2 pi radians, we can work our way backwards to any of these. All right, but that's it. Assuming these are memorized, well then 120 degrees, that's just 2 times 60 degrees. And 60 degrees is pi over 3 radians. So it's 2 times that. So it's 2 pi over 3 radians, which we can quite often just write. I'll write like this, a little bit neater. 135 degrees, that is the same as 45 times 3. It's 3 times 45 degrees. So 45 degrees is pi over 4. And so we have 3 of them, so 3 pi over 4. 150 degrees is 30 degrees 5 times. 30 degrees is pi over 6. And so we have 5 of them, so 5 pi over 6. 210 degrees, just more than a half a rotation, is 7 times 30 degrees. So it's 7 pi over 6. Now 80 degrees is the first one that doesn't relate back to one of our special angles. So I can't just quickly come up with an equivalent in radians by looking at some multiple of a special angle. So what I can do then is just look back up here and realize that when we want to kind of go back and forth between radians and degrees, this is always true. Radians divided by pi is the same as degrees divided by 180. And that's because 180 degrees is equivalent to pi radians. Remember, 360 degrees is the same as 2 pi radians. So in general, if I know an angle in degrees and I want to figure out what is in radians, I can just look at this proportion. So in this case, it'd be pi times degree divided by 180. Essentially cross multiply, or however you want to solve it. So in this case, in 80 degrees in radians will be 80 degrees times pi divided by 180. So I'll show that right here for my work. So 80 degrees, I want to multiply by pi and divide by 180, and then simplify this. 80 divided by 180 simplifies to 4/9. So I have 4/9 pi, or we can say 4 pi over 9, whatever makes you happy. And so I'll go with 4 pi over 9. And for the last one, it's the other way around. We have the value in radians. It's not in terms of pi, which makes it kind of a bit more awkward sometimes. Notice there's no unit. And in general, while you can write RAD for radians, the default really is radians. If you don't see a symbol, if you don't see a unit, we are actually meant to think in radians. So once I know I have a rotation of 1.5 and I don't see a degree symbol here or anything else, this must be in radians. And so I want to use that same proportion the other way around. This time, I want to figure out what the degrees is. And I know the radians. So if I want to turn it into degrees, I need to go radians times 180 divided by pi. And so I take my 1.5 radians times by 180 degrees, divide by pi, and I get 270 degrees over pi, and that's the exact value. It does say to express your answers to 3 significant figures, so that is approximately 85.9 degrees. So just shy of 90 degrees. All right, so before I move on, keep in mind, very, very often we work with special angles, and if we do, we can often convert and visualize these quite nicely. So in this case, I now have this object here. The angle here is 280 degrees. I want to find the exact perimeter of this. Well, one of the things we notice in this is that when dealing with radians, the arc length from here to here in radians is an incredibly simple formula. In general, if you want to find that arc length, it's always the same, if we're thinking in radians, as just the radius times theta. It's an incredibly simple formula. That's if we're thinking in radians. Right now, my angle's in degrees. So I want to convert into radians quickly, so I'll do that first. So I want to turn this into radians. So remember again, I want to take my 280 degrees, multiply by pi, divide by 180, and I get exactly, well, 280 over 180 reduces to 14 over 9, so I have 14 pi over 9. And so that's my angle in radians now, which means I can find this arc length extremely quickly. This arc length is going to be just the radius, which is 9 centimeters, times the angle, which in radians is 14 pi over 9. So how convenient. My 9s cancel out. And so I have exactly just 14 pi. Now that's not my entire perimeter, that's the arc length. All I need to do now is add this radius here and this radius here, both of which are 9 centimeters. So all I need to do now is take that 14 pi and add 18 to it. So I'll say, therefore, the perimeter of this shape is 14 pi plus 9 times 2 plus 18 centimeters. Here's my exact value. And it does ask for the exact value, so I don't want to decimalize anything. It won't be exact anymore. All right. So lastly, I have a semicircle here, and part of it is shaded. And I tell you that this is a circle with radius 1, and it's shaded from 1/2 to 1 on the x. So I'll kind of label that right here. This is 1/2, this is 1, which makes sense. It's a diameter of 1, and I want to find the area of that shaded region. All right, so how can I do this? Well, one thing that helps is to first visualize a sector from here to here. And if I look at all of this as a sector, well, I can find the area of a sector. And then I can subtract the area of that triangle, because I do have a right triangle right here. And I've got what I need. So let's first focus on the area of that sector, which we've learned about before in degrees. But when we're dealing with angles and radians, the area of a sector is simpler, is a quite a pleasant formula. It is just 1/2 r squared times theta. And so in this case, I know the radius is 1. So I have 1/2 times 1 squared times theta. So really, it's just half of theta. So the question is, what's theta? So I need to figure out theta at some point. So let's figure out theta. Theta being this angle from here to here. So let's look back at my visual here. To find this angle, what do I know? Well, I know, for example, this, I don't know the height there yet, but I do know this from here to here is the radius. So this is exactly 1. And I do know from here to here is exactly 1/2. And I know I have a right triangle here. So I can find theta using some basic trigonometry. I can use the cosine function, for example. Say the cosine of theta is adjacent over hypotenuse, or in this case, 1/2 over 1. So I can say the cosine of theta equals 1/2 divided by 1, which means the cosine of theta is just 1/2. And ideally from memory, although we could use the inverse cosine function, from memory we know that cosine of 60 degrees is 1/2. But I want to think in radians, and 60 degrees is pi over 3. So that angle there is pi over 3. So now I can find the area of that sector. That theta is pi over 3. Because remember, this formula for the area of the sector is only correct if we're thinking in radians, which gives me just pi over 6. So that's the area of that whole sector. All right, so now I want to find the area of the triangle, which should be pretty pleasant. I have, a right triangle. I need to find the height. I need to find the height from there. I could do a number of things. I could use the Pythagorean theorem. I do know we have a 60-degree or a pi/3 angle here, so I have various approaches. I'm going to just realize that this must, or I could use special triangles. How am I going to do this? I'll use a sine function here, I guess. I mean, I have so many options. But I'll say the sine of 60 degrees, or I'll stick with radians, pi/3. Although it makes no difference to think in degrees. The sine of pi/3 is opposite over hypotenuse. So in this case, 1/2 over h. Sorry, I'm using tangent right now. I could, but I'd rather not. So let's do this properly. The sine of this angle is opposite over hypotenuse, so it's h/1. There we go. That's what I'm trying to say, which means I don't really need to divide by 1. And the sine of pi/3, which you could use your calculator, same as the sine of 60, is exactly √3/2, which means that height is √3/2. Which means now I can easily find the area of that triangle. Base times height divided by 2. In this case, 1/2 times √3/2 divided by 2. So I'll write the area of the triangle, which again, base times height divided by 2, in this case, 1/2 times √3/2 divided by 2, which is √3/4 times 1/2, which is √3/8. So there's the area of the triangle. And so finally, the area of that shaded region, like I mentioned a while ago, is going to be the area of the whole sector minus the area of the triangle. And so I'll just finish off with that. I'll say, therefore, the area of the shaded region is going to be, again, pi/6, that's the larger value, minus the triangle, √3/8. And I could combine my denominators together, but why, I'm done, so I'm not going to make it more work.